Okay, let's unpack this.
Let's do it.
We are tackling a question today that isn't just monumental, it's kind of existential.
It really is. We're talking about the Fermi paradox.
And for anyone who might need a quick refresher, the core conflict is this. We live in a universe that is, it's staggeringly old. 13.8 billion years.
And just in our own Milky Way galaxy, astronomers figure there are billions of planets that are potentially habitable. Billions.
So with that much time and that many planets, you'd think life would be everywhere.
Exactly. Not just, microbial life. We're talking intelligent technological civilizations. Logic says they should have popped up all over the place.
They should be obvious.
Obvious. But as the physicist Enrico Fermi famously asked his colleagues at lunch back in 1950, where is everybody?
That's the question. The great silence. The universe seems totally empty. And that is the paradox.
And our mission for this deep dive is to go, way beyond the standard theories.
We're not just talking about the great filter today, are we?
No. We are exploring something more radical, a deeply ironic hypothesis, really.
Which is?
That the solution to the paradox isn't their absence. It's their perfect, deliberate strategy of presence.
The infiltration hypothesis.
Precisely. The idea that they are already here, hiding in a way that is so effective, so complete, that we just mistake it for normal life.
And the key to this whole thing, which is what I find so fascinating, comes from a joke, right?
It comes from the immediate sort of satirical answer that Fermi's colleague, Leó Szilárd, shot back at him right there at the lunch table.
And that legendary response was,
"They are already among us, but they call themselves Hungarians."
A joke about the incredible, almost alien intelligence of the European scientists at Los Alamos.
And that joke, as strange as it sounds, is the key. It's the central piece of the puzzle we're putting together today.
Okay, so the first big idea we have to get our heads around is cosmic time.
Everything hinges on this. The entire infiltration hypothesis falls apart if you don't grasp the chronology.
We tend to think of ourselves, of humanity, as being, right on time. We showed up when the universe was ready.
And that's just fundamentally wrong. When you look at the cosmic clock, humanity is an extreme latecomer.
A Nachzügler, I think is the term our sources used.
Yes, a straggler, a latecomer. And realizing that is the first step. The Milky Way was ready, truly ready, for complex life billions of years before Earth even formed.
Let's lock in that timeline then. The galaxy itself started forming when?
Almost right away, about 13 to 13.8 billion years ago. We're talking just a few 100 million years after the Big Bang itself.
Wow.
So that basic structure has been around for almost the entire age of the universe.
And you can think of it in phases, right? Like building something in stages.
A great way to put it. The first stage was the thick disk. That's mostly older stars, and it started coming together about 13 billion years ago.
And our sun. Where are we in all this?
We're in the thin disk. That's a later structure. It only really began to form about 8 to 10 billion years ago.
Okay, so let's put a pin in that for the listener. Our whole solar system, the sun, the earth, everything, is only 4.5 billion years old.
Exactly. So the basic architecture of our galaxy is vastly older than we are. We are infants on a very, very old stage.
And that means there was time for the right kinds of stars to form, right?
Yeah.
The stable ones you need for life.
An immense amount of time. We're talking specifically about G-type stars like our sun, and especially K-type stars, the orange dwarfs.
Why are those K stars so important for this theory?
Because they are the ultimate marathon runners. They're a bit dimmer than our sun, but they have these incredibly long, stable lives. We're talking 20, maybe even over 50 billion years.
Compared to our sun, which has about a 10 billion year lifespan in total.
Right. A K-star could theoretically nurse a planet through 5 full evolutionary cycles like ours, and the earliest of these stars started forming 13 billion years ago.
Okay, but there's always been this counter-argument, hasn't there? That those first stars were metal poor. They didn't have the heavy elements to build rocky planets.
That was the old assumption, yes. And it was a good argument for a while. It suggested life had to be a recent thing. But newer astrophysical data has, it's completely overturned that.
Oh, so?
While the very, very first generation stars were metal poor, they were also huge and burned out incredibly fast.
They went supernova.
In a big way. And when they exploded, they seeded the galaxy with their ashes, all the carbon, silicon, oxygen, and iron you need. The chemical enrichment of the galaxy was staggeringly rapid.
So the raw materials for Earth-like planets were actually available much earlier than we thought.
Much, much earlier. We're talking 12 to 13 billion years ago. And this isn't just a model. We have proof.
The Kepler 444 system.
That's the one. It's a star system that's 11.2 billion years old. And we found 5 small, rocky planets orbiting it.
That's definitive proof. Rocky worlds could and did form in the early universe.
It's a lock. The conditions were met.
Okay, so here's where it gets really interesting. Let's run the clock. If you have a stable K-star world and microbial life gets started there pretty quickly, say 500 million years after the planet forms,
A timeline very similar to Earth's.
then simple life could have been around 12.5 to 13 billion years ago.
Right. And now we apply what we know about our own planet's development.
The 4 billion year pace.
Yeah.
The time it took us to get from the first cell to, animals and plants.
If you assume that pace is roughly average, then complex life-real fauna and flora could have emerged 7 to 8 billion years ago.
And from there to a technological civilization.
It was about another 500 million years for us. So being conservative, you could say technological civilizations might have appeared around 8.5 billion years ago.
8.5 billion.
It's a number that's hard to process. If they started then, they had a developmental lead of over 4 billion years before our sun was even born.
That's just staggering. We aren't just late to the party. The party was over, and they were cleaning up before we even got the invitation.
It changes everything. We think about progress in terms of centuries or maybe millennia. What does a continuous 4 billion year technological head start even look like?
It's not just better iPhones. It's a different kind of existence.
It's a phase transition.
Yeah.
Their science would be indistinguishable from magic to us. They would have mastered energy, biology, maybe even physics in ways we can't comprehend.
Which brings up the obvious question. If the galaxy was potentially teeming with this kind of ancient life for billions of years, why did we take so long? Why are we the Noctugler?
And this is where it gets really specific and kind of ironic. The reason for our delay probably isn't some universal great filter out there in the cosmos.
It's something local, something right here at home.
Exactly. Our sources point to a very specific and deeply strange mechanism in our own Earth-Moon system, a mechanism that basically hit the pause button on our evolution.
For a billion years, the boring billion.
That's the one. Geologists call it that. It was a long phase from about 2 billion years ago to 600 million years ago where evolution just stalled.
And the main symptom of that stall, the thing we can actually measure, was the length of Earth's day.
Yes. For nearly a billion years, the day was locked, solid, stuck at around 19 to 21 hours long. And to understand why that stopped evolution in its tracks, we need to talk about a sort of cosmic tug-of-war.
Between the Earth, the Moon, and the Sun.
That's the game. We all know the Moon acts as a brake on the Earth's rotation, right?
Right. Tidal friction. The Moon's gravity pulls on the oceans, creates a bulge, and that bulge creates friction as the Earth turns, slowing it down.
A perfect description. And as it slows the Earth, the Moon slowly drifts away from us, about 3.8 centimeters a year. It's why our day has lengthened from maybe 6 hours in the past to 24 hours now.
So the day should have just kept getting longer and longer, steadily.
Yeah.
But it didn't. It got stuck. Why?
Because the sun was secretly pushing the other way. It was acting like the planet's gas pedal.
How does the sun accelerate the Earth's rotation?
Through the atmosphere. The sun heats our atmosphere, which creates these massive thermal tides, basically huge bulges of air. And these bulges create a tiny, tiny torque that pushes the Earth's spin forward.
But if the moon is braking and the sun is accelerating, shouldn't they just balance out?
They do now, more or less. But back then, something special happened. When the Earth's rotation slowed down to that sweet spot, that 19 to 21-hour day, the atmosphere's natural frequency of oscillation.
It's called the Lamb wave, right?
The Lamb wave. It hit a perfect state of resonance with the sun's heating cycle.
Okay, so it's like pushing a kid on a swing, if you time your push just right.
A tiny push creates a huge effect. The resonance dramatically amplified the sun's accelerating torque. Suddenly, that tiny push was strong enough to perfectly counteract the moon's massive brake.
And the day just froze. A perfect equilibrium.
For a billion years. And we can read this history in the rocks. In geological formations called tidal rhythmites, you can see the layers left by ancient tides, and they confirm this long, long plateau in the day's length.
It's incredible that we can even know that. But what's the biological consequence? Why is a 21-hour day bad for evolution, but a 24-hour day is good?
It all comes down to oxygen.
The great oxidation event.
Or rather, the thing that was holding it back. Complex life, animal life, needs a lot of oxygen. It's a high-energy fuel. And the key to pumping huge amounts of oxygen into the atmosphere was a longer day.
Why? What does a longer day do?
Two things. First, longer periods of uninterrupted daylight mean more photosynthesis from the cyanobacteria in the oceans.
More sunlight, more oxygen. Makes sense.
But the bigger effect is on ocean mixing. A longer day creates a bigger temperature difference between the day side and the night side of the planet. That drives stronger ocean currents and more nutrient upwelling from the deep sea.
And those nutrients are food for the cyanobacteria.
It's fertilizer.
Yeah.
So because the day length stalled out, the oxygenation of the planet also stagnated. It held back the evolution of complex animal life, delaying the Cambrian explosion by a massive margin.
So the very Earth-Moon system we credit with making Earth so stable was also, ironically, the reason we were held back for 1 billion years.
A stunning cosmic irony. And it opens the door to a fascinating what if.
The turbo counterfactual. How could we have sped things up?
It's surprisingly simple. Imagine a moon with just 1.5 times its current mass.
Not a huge change, cosmically speaking.
Not at all, but that would have given it a much, much stronger tidal braking force.
A stronger break.
A brake so strong that it would have just overpowered the atmospheric resonance. The sun's little push from the Lamb wave wouldn't have been enough to stop it.
So the day length would have just kept increasing, right past that 21-hour stall point.
And we would have reached the oxygen levels needed for complex life maybe 1.5 billion years earlier.
1.5 billion years. So we could have been on the scene 7 or 8 billion years ago.
We could have been one of the early ones. The conclusion is pretty unavoidable. Our complexity was delayed by a local and very specific physics problem, which makes it even more likely that early starters on other less quirky worlds are out there.
And if they have a 4 billion year lead on us, plus our 1.5 billion year delay, we have to ask, why aren't they talking to us? Or maybe, what have they learned in that time that makes them not want to?
And that transition in thinking it's just critical. If you accept they are billions of years ahead, you have to accept that their communication methods have evolved beyond our wildest dreams.
The silence isn't an absence of life. It's a sign of maturity.
Exactly. This completely challenges the basic assumption of SETI, which for decades has been listening for, big, powerful radio signals.
Right, like the Arecibo message. We're basically shouting, hello into the void with radio waves.
Our sources call that the technical adolescence phase. It's this cosmically brief window, maybe a few hundred years, where a young civilization uses loud, inefficient, and frankly insecure broadcast methods.
Okay, I get the inefficiency part. It takes a huge amount of energy to blast a signal in all directions. But what's insecure about it?
Think about it. If you've managed to survive for billions of years, you've learned that the universe can be a dangerous place. Broadcasting your exact location, your technological level, the composition of your planet.
You're painting a giant target on your back.
For any potential competitor or predator, a mature civilization learns very quickly that silence is the best defense.
And there's the distance trap, too.
The distance trap is devastating to the idea of radio communication. By the time a signal from, say, 1,000 light years away reaches us, the civilization that sent it is 1,000 years more advanced.
They moved on. The message is a relic.
It's an ancient artifact. They've likely transitioned to entirely new physics. It's like we're waiting for a message sent by drumbeat in a galaxy that's running on a fiber optic network.
That's the analogy from the sources, isn't it? We're listening for Trommelschlag in a galaxy full of glass-faster nets.
Yes. Drumbeats versus fiber optics. A mature civilization prioritizes efficiency and security. They're not broadcasting. They're using tight beam, point-to-point communication.
So what would that look like? If not radio, then what?
Well, you'd want something that doesn't interact much with all the gas and dust between the stars. Something like a tightly focused beam of neutrinos.
Neutrinos.
Yeah.
The ghost particles.
Exactly. They pass through planets, stars, anything, almost without a trace. That makes them perfect for a secure, long-distance data link. We can barely even detect natural ones, let alone a modulated, information-rich signal.
Or even more advanced, they could be using gravity itself.
Modulated gravitational waves. We've only just confirmed they exist from things like black hole mergers. The idea that a civilization could generate and control them to send information is, well, it's deep into theoretical physics for us.
But for a billion-year-old civilization,
It might be trivial. And then there's the ultimate method, quantum entanglement.
instantaneous communication across any distance.
If they've cracked that, then light-speed communication is obsolete. Why wait thousands of years for a message if you can have a real-time conversation?
And even if we were looking at the right part of the spectrum, there's the data density problem.
Right. Their signals would be so perfectly compressed and encrypted that to our instruments, they would look exactly like random cosmic background noise.
We're listening for a simple beep 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 pattern, and they're sending the entire Library of Congress in a millisecond burst of what looks like static.
So we miss it. We just filter it out as noise.
So if listening for their hello is a dead end, we have to shift our strategy. We have to look for their exhaust fumes.
That's the move to SETIT, the search for extraterrestrial technology. You look for the unavoidable byproducts of massive energy use because they can't cheat thermodynamics.
Energy use always creates waste heat.
Always. And if a civilization is using truly vast amounts of energy, like a Kardashev Type 2 civilization,
One that's harnessing the entire output of its star.
they'd likely do that with a megastructure, something like a Dyson swarm, a huge cloud of solar collectors orbiting their star.
And that structure would have to radiate its waste heat into space.
Exactly. So the star itself would look strangely dim in visible light because its light is being captured, but it would glow unnaturally brightly in the mid-infrared spectrum.
You would have a heat signature that makes no sense.
A massive anomalous heat signature. And observatories like the James Webb Telescope are actively looking for exactly that kind of strange infrared excess right now.
And beyond heat, we can look for chemical pollution.
Unmistakable chemical fingerprints of industry. The best candidates are artificial gases that have no known natural source. Things like chlorofluorocarbons, FCKWs.
The stuff from old refrigerators and spray cans.
The very same. What makes FCKW so good as a technosignature is that they are incredibly stable, they don't break down easily, and they don't get scrubbed out of an atmosphere naturally.
So if a civilization has an industrial phase like ours, they might pollute their atmosphere with this stuff, and it would just hang around.
For millennia. A clear, lingering chemical fossil of their technological adolescence visible to our telescopes from light years away.
So their silence, it's not empty. It's a calculated strategy, born from efficiency and a deep, deep understanding of risk.
And the biggest risk of all, the one that builds the highest wall, is biological.
Okay, this brings us to what might be the most terrifying part of the hypothesis, the absolute biological wall.
This is where the idea of a friendly first contact shaking hands on the White House lawn just completely falls apart.
Because it's not a diplomatic problem. It's a biosafety catastrophe for everyone involved.
And it's based on something incredibly fundamental, the literal handedness of life's molecules, the concept of chirality.
Like our left and right hands. They're mirror images, but you can't lay one perfectly on top of the other.
Precisely. And all life on Earth, every single microbe, plant, and animal is homochiral. We are built on a single, consistent pattern.
Our proteins use left-handed amino acids.
Exclusively. And our DNA and the sugars we use for energy are all right-handed.
The whole system is locked into that L-amino D sugar configuration.
Billions of years ago, a choice was made, and now our entire biology, from digestion to our immune system, is based on it. So what happens if an alien life form evolved using the exact opposite? Mirror image chemistry.
D amino acids and L sugars.
The consequences are immediate, and they are disastrous.
But wait, if they're so advanced, couldn't they just engineer a solution? Create some kind of universal antidote?
They could create a sterile room, but they can't rewrite fundamental chemistry on the fly. It's a lock and key problem. Their enzymes, their biological tools are shaped for a right-handed key. Our biology is a left-handed lock. They just don't fit.
So if they tried to eat our food?
An apple, for instance. Their digestive enzymes wouldn't recognize the molecules. It would be completely indigestible biological plastic.
You would just pass right through them.
Providing zero nutrition and potentially being highly toxic, they would starve to death with a full stomach.
A horrifying thought. But the danger to us from them is even greater, isn't it?
Far greater. We're talking about the winner-takes-all scenario. Imagine a simple, competitive microbe from their world with D-chirality.
Right.
It would have a kind of biological stealth technology. Because its molecules are mirrored, it would be completely invisible to our entire immune system.
Our antibodies, our T cells, nothing would work.
Nothing. Our antibodies are shaped to latch onto L proteins. They literally do not have the right glove to grab onto a D protein invader. Every virus on Earth, every predatory bacterium is configured to attack L life. This alien microbe would be, for all intents and purposes, unkillable by anything on Earth.
But if it can't digest our proteins, how does it harm us?
It wouldn't eat our cells directly. It would compete for the raw materials. It could still absorb raw carbon, nitrogen, and phosphate atoms from the environment and use them to build more of its own mirrored structures.
It would starve our ecosystem.
Silently and efficiently. And the waste it produces. That's the other nightmare.
Mirror image waste.
Which no Earth-based bacteria or fungi could decompose. They don't have the right enzymes. So you'd get this massive planetary accumulation of sterile, unrotting biological garbage.
Choking the entire planet. An ecological suffocation.
It could lead to a total replacement of our biosphere. Not an invasion, but a replacement.
And that's the worst-case mirror biology scenario. Even if their chemistry was compatible, just different, it's still a disaster.
Yes, that's the American scenario, a direct historical parallel.
When Europeans arrived in the Americas,
Up to 90% of the indigenous population died, not from war, but from diseases like smallpox and measles. Diseases that were trivial to the Europeans who had co-evolved immunity.
but were catastrophic to a population with no exposure.
Now scale that up to a cosmic level. An alien cold, something their species barely notices, could hit a human population with zero evolved defenses. It would be an unstoppable pandemic.
And here's the critical reversal. That threat is mutual. From their perspective, we are the biohazard.
Absolutely. Earth is a giant, uncontained biological threat. To them, we are Keimschloder.
Germ throwers.
Or sickness catapults. Our common flu could be an extinction-level event for them. So any truly advanced civilization, one that survived for billions of years, would understand this risk. They would see direct organic contact as insane.
So total biological separation is the only sane strategy.
It's the only responsible path. If they're here, they are not here in person.
Which leads us directly to the elegant solution. If you can't come yourself, you send a proxy.
This is where all the threads converge. You have the technological maturity to abandon radio, and you have the biological imperative to maintain quarantine. The result is the Avatar Protocol.
And the goal isn't conquest, it's anthropology.
Exactly. A very old, stable civilization would be fascinated by a young, volatile one like ours. They'd want to study our sociology, our technology, our art. They want data, not territory.
So to get that data without risk, you use sterile, expendable proxies.
Right. And these proxies have to be completely sterilized before they're ever deployed on a planet. Heat, radiation, whatever it takes. No cross-contamination.
And the sources suggest two main models for these avatars, depending on what they're trying to do.
The first is the one we all know from pop culture, the functional drone, the gray alien.
Let's talk about the design of the gray. It's not random. It's engineered for a purpose.
It's pure function over form. They're small because mass is expensive to move between stars. They have those large black eyes, which are probably multi-spectrum optical sensors.
Designed to gather as much data as possible.
In any light condition.
Yeah.
And their biology is reported as being minimal. No reproductive organs, no obvious digestive tract.
They're basically low-mass biological robots, field technicians.
Perfectly optimized for data collection and long-duration space travel. They're not here to blend in. They're here to do a job and leave.
But for deep, long-term study, you need something else, something that can blend in.
For the really high-stakes observation, like guiding a species through its nuclear infancy, you need the second model, the perfect infiltrator.
And this is where it gets really unsettling.
This is the truly elegant and disturbing solution. You genetically engineer a proxy that is a perfect biological mimic of the target species.
So it looks human, acts human, and crucially has the same L-chirality biochemistry as us.
Which means it can eat our food, breathe our air, and exist within our society without any risk of biological contamination. It's biochemically compatible.
And its mission isn't just to watch, it's to guide.
To subtly influence events at critical junctures. To nudge humanity away from self-destruction during dangerous technological thresholds, like the invention of the atomic bomb, or perhaps advanced AI.
They're cosmic guardians, or maybe cosmic babysitters.
And because they are perfect L-chirality mimics, finding one would be almost impossible with today's technology.
You do a blood test, a DNA test, it all comes back as 100% human.
There's no medical or forensic test we have that could spot one.
So how could we even begin to look if they're perfect? Where's the flaw?
You'd have to go deeper than biology. You'd have to look at the atoms themselves.
Isotopic analysis.
Right. Every planet has a unique isotopic fingerprint. The ratio of, say, carbon-12 to carbon-13 in our bodies is a direct result of Earth's specific geology and biology.
So an avatar built in a lab on a spaceship or synthesized on another world.
Might have slightly different non-terrestrial isotopic ratios in its atoms.
Huh.
You'd have to do an incredibly sensitive analysis of their tissue to find it. It's atomic detective work.
And the other way to find them.
You look for their connection home, the umbilical cord.
You have to be sending all this data back to a mothership or some kind of base.
Constantly. So you'd look for that data stream. It wouldn't be radio. It would be a super high frequency, tightly beamed, perfectly encrypted signal.
The kind of signal we would probably just dismiss
As background noise. A glitch, a distant pulsar. We might be seeing their communications all the time and have absolutely no idea what we're looking at.
Which brings us all the way back to where we started. The final perfect irony at Los Alamos.
We have to return to that lunch in 1950. To Szilárd's joke. They are already among us, but they call themselves Hungarians.
And that wasn't just a throwaway line. It was a genuine reflection of how the American scientists felt about these European physicists.
People like Szilárd, John von Neumann, Edward Teller, their intelligence was perceived as being almost off the human spectrum. They could see solutions to problems instantly, as if they were running on a different kind of processor.
They were jokingly called Geturnte Marcianer.
Camouflaged Martians. Because their genius was so profound, it seemed, well, alien.
And this joke is the key to the ultimate hiding strategy, isn't it?
It's the ultimate misdirection. The most effective way to hide isn't to be invisible in the shadows. It's to stand in the brightest spotlight, to be so brilliant and so essential that no one would ever think to question you.
Achieve normality. Perfect normality.
You blend in by being exceptional. If your goal is to guide humanity through its most dangerous moment, you don't hide in a cornfield in Iowa. You go to the heart of the action. You go to Los Alamos.
You become indispensable.
And this is where the irony folds in on itself when we look at Enrico Fermi, the man who asked the question.
His nickname was the Navigator.
Because of his uncanny ability to solve incredibly complex physics problems in his head with almost no data. He would just see the answer.
Again, like he was running on a different kind of processor.
He fits the profile of a perfect guiding infiltrator almost too well. He was at the absolute center of the atomic age, guiding the project, and he possessed a cognitive ability that baffled his own brilliant colleagues.
So the infiltration hypothesis suggests that his question, where is everybody?
Was the greatest misdirection play of all time.
By asking the question himself, he focuses all future investigation outward, to the stars.
Deflecting any and all suspicion away from the very center of the scientific revolution, away from the people doing the guiding, and perhaps away from himself.
We're looking for loud, obvious signals from deep space.
While the highest intelligence is using subtle strategy, hiding in plain sight, their silence isn't absence. It's the mark of a perfect plan.
Okay, let's wrap this up. Let's review the key takeaways from this deep dive.
The Fermi paradox has an answer, but it requires us to completely flip our assumptions.
First, we are the latecomers, the Nachtjagler. The galaxy was ready for life billions of years before we were.
Our delay was local. The Earth-Moon system got stuck in a resonant lock, the boring billion, which stalled the oxygenation of our planet and put our evolution on hold.
Because of that immense age gap, any ancient civilization would have abandoned radio long, long ago. We're listening for drumbeats in a fiber optic galaxy.
Our search needs to shift. We should be looking for the unavoidable byproducts. The waste heat from a Dyson swarm, or the lingering atmospheric pollution of FCKWs.
And finally, the absolute showstopper for open contact is biology. The molecular handedness, the chirality of life, makes any direct interaction a potential extinction-level event for both sides.
Which means total separation using sterile avatars is the only logical and responsible strategy for them.
The ultimate camouflage isn't invisibility. It's being so brilliant and essential that you become part of the normal fabric of history.
Right, so what does this all mean? Here's the final thought for you to mull over.
If a civilization with billions of years of experience wanted to guide us, they'd use perfect human mimics. And the best place to hide that mimic
would be to make them so critical, so central a navigator for humanity's atomic birth that no one would ever suspect.
We're listening so intently for a message from the stars.
Maybe the silence is the message. Or maybe we need to stop searching so far outside ourselves and instead look a little closer at the people who first asked the question.